The article I chose for this project uses the coronavirus pandemic to emphasize the possibilities of computer-aided drug design with the goal to efficiently identify potential drug repurposing options. Drug repurposing uses medications that were previously developed for other diseases to treat a new disease like COVID-19. In order to determine which drug could be a candidate to treat COVID-19 in computer-aided drug design, scientists use a crystal structure of the virus and run it through various software and databases to find a good match. In the article, they found that each drug has 3 drug targets, and each drug target has 4.7 drugs. This shows how polypharmacology is actually a common occurrence and may support the idea of drug repurposing. Additionally, this study also shows how efficient it can be to find potential drug matches for COVID-19 in a matter of 5 days or less. So the top picture shows a few characteristics that are analyzed in the different programs that are used in drug development. These characteristics determine what will make a good candidate for the particular virus, some of which are docking, analyzing molecular interactions, evaluating the binding strength, estimating drug-like properties, and each of these characteristics are tested by a different program. However, these programs have both their pros and cons. Some are efficient due to having a large database, however not very accurate, whereas some programs may be much more accurate at the expense of losing its efficiency. Therefore, in this study, they developed a system of what they called hierarchical virtual screening, or HVS for short. HVS defined the proper sequence to which they would use different programs to test on COVID-19 in order to narrow down the results after every test, as well as to balance the efficiency and accuracy. Using this method, the scientists wanted to find drugs that could be repurposed to target and inhibit the COVID-19 protease. For example, they found in this study through HVS that the drug lopinavir, which is an inhibitor of HIV-1 protease, passed the first test of a promising docking simulation. Therefore, they moved this drug into a molecular dynamic simulation where they found drugs that had good binding free energies and were structurally similar to lopinavir, which is shown in the bottom picture. And the bottom picture came from figure 1 in the article, and it shows the structural similarities between one another, as well as what each drug was initially designed for. So such as being a selective proteasome inhibitor, chemotherapy drug, an antiviral drug for hepatitis C, or protease inhibitor for HIV. And then moving through the next phases of HVS, they concluded that these 5 drugs shown were actually identified to have inhibitory effects against COVID-19 protease. Along with finding a cure for COVID-19, scientists are also testing samples sent from hospitals in order to make diagnoses. And to begin the coronavirus testing process, a sample from the patient must be obtained. This sample can be taken from swabbing the nasopharynx or oropharynx, which is shown in the top left picture. Or they can collect a sample of sputum from the patient, and these are the most common methods. And then polymerase chain reaction, or PCR, is then used to test the specimen. Polymerase chain reaction is an in vitro method of producing multiple copies of a specific DNA segment. This process undergoes 3 temperature phases shown in the picture of denaturation, annealing, and extension. The purpose of the first phase is to denature the DNA and separate its strands by adding heat. The temperature is then lowered in the second stage of annealing. The temperature is lowered to about 55 to 65 degrees Celsius. The annealing temperature is based on the melting temperature of the particular primer that is being used in the PCR. The effect of lower temperatures allows the primer to attach to the template DNA. And lastly, extension involves a raise in temperature to about 72 degrees Celsius, which allows proper extension of the primer and DNA synthesis. There are different types of PCR that vary slightly. For the diagnosis of coronavirus, laboratories test the sample by running it through reverse transcriptase real-time PCR. Reverse transcriptase is needed because the genetic information of COVID-19 consists of RNA. The role of reverse transcriptase is to turn RNA into DNA by first transcribing it into cDNA or complementary DNA. The cDNA is used as a template for the real-time PCR reaction. The difference between traditional PCR and real-time PCR is that traditional PCR uses agarose gel at the final phase, or where the PCR will start to plateau, to then detect for PCR amplification. However, real-time PCR can be measured during the growth phase of replication, and therefore results can show the relationship between the amount of the starting target sample and the amount of PCR amplification at any particular cycle. And these unique results of real-time PCR provides more accuracy and precision than the traditional methods. So to clarify, let's say this 30th cycle was its end stage or its plateau. This is where traditional PCR would read the result. But however, for real-time PCR, let's say you wanted to look at the 3rd cycle and just see what the amplification looks like there. You could do that. Or you could do it on the 15th. It doesn't matter which cycle, or if it's at the end of the PCR cycle, to find the amplification. So before this project, I had no idea about computer-aided drug design. But now that I've learned a little about it, I started to think about the benefits versus limitations of using technology for drug discovery, especially since it's not a widely accepted method. Traditional methods of drug discovery can be biased because scientists rely on pre-existing knowledge of potential drug targets. However, with the computer, it is able to go beyond and potentially find targets that scientists may have overlooked. Using technology for drug discovery also saves a lot of time, which is absolutely vital during a pandemic. Although some limitations to computer-aided drug design include that the accuracy of predictions are entirely based on how well the algorithm is put together by the creator. Also, there is a possibility of an algorithm bias, where the scientists subconsciously relay their ideas and predictions into the algorithm. And of course, if this were to be the future of drug design, predictions made by the computer would still have to be tested by scientists to ensure that they are valid. This ability to question research and see how it can be capitalized on or recognize the possible implications is what I've gained from being a biology student at FranU. What I've taken away from biochemistry alone is almost like a second language. Before I enrolled into any biochemistry class, I would often have assignments that required me to analyze or present a journal article. I used to have to look up a lot of definitions, functions of different enzymes, pathways, etc. But since taking biochemistry, I can generally look at any journal article about the body and recognize familiar terms as well as get a good understanding of the article much faster. I've also noticed that my knowledge grew tremendously just by taking biochemistry, neuro, organic 2, and pathophysiology within a year of each other, which is essentially because there was an overlap of these same concepts in these different classes, but each class would look at it from a different angle.